Welcome, students. We've been looking at exponential functions and logarithmic functions and exponential equations and logarithmic equations for several classes now. And today what we're going to do is we're going to look at several application problems involving exponential and logarithmic equations. In fact, the following lessons will also include situations that are modeled off of exponential functions and logarithmic functions. The reason we're going to take so much time to look at different examples is because there's a lot of real-world things that are modeled off of exponential or logarithmic functions, and we've never really been able to deal with them mathematically before, but now we have the tools to do so, and so we really want to take the opportunity to look at various example problems. So in this video, we're going to look at one application problem, and then in the next video, we'll do another, and then of course, there will be a few more linked below. Let's start. The velocity of a skydiver, t seconds after jumping, is given by v equals 80 times the quantity 1 minus e to the negative 0.2 t, measured in feet per second. How fast is the skydiver falling after 3 seconds? After how many seconds is the velocity 70 feet per second? Let's take a look at these questions one at a time. First, how fast is the skydiver falling after 3 seconds? In this case, we're looking to find the velocity when t equals 3. So all we need to do is substitute in 3 for t and then evaluate this function. So we have v equals 80 times 1 minus e to the negative 0.2 times 3. And negative 0.2 times 3 is negative 0.6. So that becomes e to the negative 0.6. And when we use a scientific calculator to get an approximation, we end up with 36.0951. And we weren't asked what to round to, so let's just round to 1 decimal point, because I don't think we need to be more specific than that. So this becomes about 36.1 feet per second. So after 3 seconds, that skydiver is falling at a rate of approximately 36.1 feet per second. For the second question, after how many seconds is the velocity 70 feet per second, instead of substituting in a value for t and solving for v, we're given the velocity that we want and we need to solve for the time. So in this case, we end up with 70 equals 80 times 1 minus e to the negative 0.2 t. So we want to eventually get t alone, but before we can do that, we want to get this exponential expression alone so that we can put it in logarithmic form and solve. So the first thing we want to do is get rid of this 80, which we can do by dividing both sides by 80. 70/80ths reduces to 7/8. So we have 7/8 equals 1 minus e to the negative 0.2 t. Now to get the exponential expression alone, we need to get rid of the 1. So we're going to subtract 1 from both sides. Now 7/8 minus 1 is the same as 7/8 minus 8/8, which gives us negative 1/8. So we've got negative 1/8 equals negative e to the negative 0.2 t. And we want to get rid of the negative in front of the exponential expression, and we can divide both sides by negative 1. That effectively gets rid of both of these negative signs. So we've got positive 1/8 equals e to the negative 0.2 t. And if we rewrite this in logarithmic form, The base is e, and so we have ln of 1/8 equals negative 0.2t. And to get t alone, we just need to divide both sides by negative 0.2. And that gives us t alone. It's ln of 1/8 over negative 0.2. That is an exact answer, but we probably want an approximation here, because we're asked after how many seconds is something happening. And if we say this many seconds, someone might look at us like we're a little bit crazy. And so we enter this expression into a scientific calculator to get an approximation, and we end up with 10.3972. And if we round to the nearest tenth, we get about 10.4 seconds, because this is an amount of time. And so after about 10.4 seconds, we will reach a velocity of 70 feet per second. Those are our final answers, but I do want to take a moment to talk about why the velocity is modeled off of a function that includes an exponential expression inside. Now here is a graph of the velocity function as a function of time. We know that the moment that the skydiver jumps out of the plane, they are moving at a speed of 0 feet per second. But then as they fall, their velocity gets higher and higher. But there's a maximum velocity that that person will reach, and that's because the wind resistance gets higher and higher as they fall, and there is a terminal velocity. Every object that falls increases in its velocity until the force of gravity downward is equal to the air resistance that's pushing upward, and at that point it doesn't move any faster. And in this point we can see that our function is asymptotically approaching 80 feet per second. And so in this case, the skydiver's speed is approaching that, and it keeps getting closer and closer, but never gets higher than that. And we've seen that exponential functions have horizontal asymptotes, and we have some transformations that are going on. We've got a vertical reflection and a horizontal reflection and some stretching and some shifting and whatnot. But basically, when we have a quantity that's growing, but it's getting closer and closer to an amount and never reaching it, it's asymptotically approaching it, oftentimes these quantities are modeled off of exponential functions. And so this is one situation where an exponential function models a real-life scenario.